thanks to the organizers for this invitation to this very nice conference and this very nice city. So Vlad was asking me for my title, so I kept it such that I could change my mind later on. So I'll talk about some topics. The topic that was mentioned in the abstract, I'll start tomorrow. I'll be talking about something a little bit different today. So what I'll be talking about is broadly localization in random structure. So this is something I have been interested in for a while and motivated by certain problems that I will describe. So I'll first give an overview of what the problems are and what the issues are, and then I'll try to give you a little bit of an outline of the approach or why this phenomenon happens. So I'll not tax your brain too much. There are too many very difficult courses going on here. So I'll try to keep things simple. Okay. So consider Hamiltonian systems. You have n particles, and they have positions at time t, q1 to qn, and momentum of these particles are p1 to pn. And the Hamiltonian is any function h of these positions and momentum. And Hamilton's equations say the following, that the rate of change of a momentum over time is minus del h del qj, and the rate of change of the position is del h del pj. So these are Hamilton's equations. Okay. So a simple example is the following: 1 over twice m. So m is the parameter that is the mass. Summation pj squared plus a potential. So m is this mass and v is the potential energy. Okay. Okay. So if you plug this in here, we recover what are called Newton's equations, second law. So you have rate of change of the position is the momentum divided by n, and rate of change of the momentum, that's mass times acceleration. So this is the force. Okay. So these are Hamiltonian flows. So these are 2n variables, and they're flowing over time, and these equations govern the flow. Okay. Now, a Hamiltonian flow has various conserved quantities. A conserved quantity is a function of the momenta and the positions which do not change over time. Okay. So one example is this Hamiltonian itself. Okay. So if h is considered to be the energy, so what I wrote down in the previous slide is just a sum of the kinetic and potential energy. So that's just one example. So this Hamiltonian is always conserved. And you have this famous Noether's theorem, which relates conserved quantities to symmetries of the system. And if all these conserved quantities are known, then this one notion of integrability, so the system is integrable. What?
This one's stronger. It's a stronger point term.
Oh, okay. No, but I'll be confused with two things. So, okay. So this is rarely the case that you know all the conserved quantities, but often you know some of them. Okay. Okay. So is this clear? What is probably most of you already know all this, but anyway. So you have these Hamiltonian flows, and they have conserved quantities, and the system is integrable if you know the conserved quantities. So there is you can represent it in an alternative way. Using complex valued functions. So you have the position and the momentum, and you can combine them formally in a position plus I times the momentum, where I is square root of minus 1. So in this case, the equations just become this: I times del psi j d psi j dt. So the rate of change over time of this complex valued thing is just the derivative of the Hamiltonian with respect to psi j, which just means this. Okay. So that's another way of writing Hamilton's equations in terms of complex valued variables. Okay. So you have this. Okay. So an example in this complex setting. So consider the Hamiltonian h of psi 1 to psi n as sum of psi j plus 1 minus psi j squared. So you are identifying n plus 1 as 1. So you're looking at the cycle. And you take the difference modulus squared. So these are complex variables, so this is a modulus squared. And if you take this Hamiltonian, then the equations become I times the rate of change of psi j is just this, minus psi j plus 1 minus twice psi j plus psi j minus 1. Okay. Okay. So this is something familiar, right? This is the second differential. So you take the psi j's and you take the second derivative, and this is what you get. And if you take a scaling limit of this, in some sense, you take a cycle and then you bring the points closer and closer together and increase the number of points. This system goes to this limit. I times del psi del t is minus Laplacian of psi. So this becomes a Laplacian. And you can easily generalize to higher dimensions. So in one dimension, it's just a second derivative. Okay. So this Hamiltonian, in the sense that I described before, gives this gives Schrodinger equation. Okay. So in this sense, the Schrodinger flow may be called an infinite dimensional Hamiltonian flow. So here, there is two variables x. So there is an x which takes the place of this j here with this Hamiltonian. Okay. Integral of gradient psi squared. Okay. So we started with h of positions and momenta, and then we combined position and momentum into one variable, complex variable, and we defined Hamilton's equations. And then you have, with this Hamiltonian, you get this flow, okay, which in the limit becomes this. So in some sense, you can make it precise. This is a Hamiltonian flow with this Hamiltonian. Okay. Any questions? Okay. A slightly more complicated example is what is a very well-known nonlinear PDE. Is the nonlinear Schrodinger equation, where you have the ordinary Schrodinger equation plus a nonlinear term. Okay. So here kappa is a parameter which is either +1 or -1. P is called the nonlinearity parameter. Psi is this flow evolving over time, where x is a space variable and t is a time variable. Okay. So that's the nonlinear Schrodinger equation. That's one form, the simplest form of the nonlinear Schrodinger equation. And this is one of the, the PDE people, they study these various equations, and this is one of them, which is widely studied. It's a prototype of, nonlinear dispersive equations. And it is important to understanding a variety of things of which I don't know much, but this is what I read. Okay, so in particular, this has all these, it arises in all these things, and there are some rigorous justification for this physical connections also. The case kappa equals +1 and -1 are, the two cases are quite different. So +1 is called the defocusing equation, and the -1 is called the focusing equation for various reasons. And this is much better understood, the defocusing, rather than the focusing equation. And just like the Schrodinger equation, this is also an infinite dimensional Hamiltonian system with this Hamiltonian. So for the Schrodinger, you just had this Hamiltonian, but now you have this nonlinear term too. Okay? So you have this nonlinear term, and p is bigger than 1, strictly bigger than 1. So this has a significant effect. Okay. Any questions? Okay, so we have defined Hamiltonian flows, and we have gone to the complex thing, and then we have shown, how these classical equations, the nonlinear Schrodinger or the Schrodinger equation, arise as Hamiltonian flows. Okay, so in particular, if you let psi flow according to this equation, this thing remains conserved over time. This doesn't change over time. Okay, so this is one very simple fact that you can prove. Okay, so where is probability here? Okay, so one of the motivations for this whole thing that I'm going to describe is this little thing that you have here, The long-term behavior of these nonlinear Schrodinger equations is, there are not many rigorous results. I mean, there are many rigorous results, but not really what people would like to prove. Okay, so it's many people are studying these things, and one of the the main open problem here is what at least Tao calls the soliton resolution conjecture, but it's other people sometimes call it the Grant conjecture here or whatever. I mean, so what this says is that for generic initial data, not for all initial data. So the initial data is the function at time 0. For generic initial data, as time goes to infinity, this nonlinear Schrodinger flow decomposes into a finite number of solitons that go away to infinity from each other, maybe just one. So I'll tell you what that means. Okay, so before that, just let me tell you what happens with the ordinary Schrodinger equation. With the ordinary Schrodinger equation, if you start with any function, as time progresses, just like the heat equation, the function will become more and more flat. Okay, the L infinity norm will go to 0. The L2 norm will remain conserved, so that's one property of these things. But the L infinity norm will go to 0. However, for the nonlinear Schrodinger equation under certain conditions, you expect a bump to remain. It may be a traveling bump, but it will remain. And there is a very precise conjecture about what kind of a bump it is. It will be a soliton, okay, in the limit. In the limit, it will be a soliton. And what is a soliton? In the simplest term, in this context, is a solitary, is a stationary wave of this form. So there is a space part and there is a time part which comes out only in the phase. So if you take the amplitude, it's constant. So it's Vx times I omega t. And if psi is to satisfy the NLS equation, then V must satisfy this. Okay. So this is the main interest is in this function V. So that's also called a soliton. And this is stationary. This is not moving, but you can easily make it moving. So you can do a time translation, and then you can. It's called Galilean transform, and you can make it move, but the shape will remain. So the shape will just be what it is. So what this conjecture says is that for most initial data, there are exceptional initial data for which this doesn't happen, but in most cases, you will have that as time goes to infinity, you will get things like solitons, which become more and more like solitons going out, and nothing else remains. So everything else just disperses, radiates to infinity. Okay. So okay, here is where probability comes in. Okay. It says generic initial data. And if you look at this blog entry, it will say this is the hardest hurdle to proving this theorem, because it's not supposed to hold for everything. So PD theorems are almost always about everything. So you do the worst case analysis. But here it says that for most, and it's not clear what is meant by most. Okay, it's not clear, and it's not a very precisely stated conjecture. It's vague, so it's not clear. So it's up to you how you define what is meant by most initial conditions. And of course, one naturally thinks that maybe with respect to some natural probability measure, if you choose. In a few special cases, it's rigorously verified. So for instance, if your initial data is close enough to a soliton, then you will have a soliton eventually, and similar things. So these things are done, but not in general. So one approach that is appealing to a probabilist to understand this long-term behavior is through the study of invariant measures. So we'll talk about this. Okay. So you have a Hamiltonian flow, just like any flow. It will have invariant measures, and if you can understand these invariant measures, you will have, if you're lucky, they'll be ergodic, but that's rarely. You can have these as ergodic, but they'll be invariant in any way, in any case. So maybe if you're lucky, you will get some information. Okay. Any questions? Okay. So a very important property of a finite dimensional Hamiltonian flow, so for n particles, is that it preserves Lebesgue measure. So this is called Liouville's theorem. And what this theorem implies is that if you take a manifold, if you take some of the conserved quantities and you consider the manifold where these conserved quantities take some specified values, then on this manifold, if you take the uniform probability distribution, okay, so that's like the normalized Lebesgue measure on that manifold, then this theorem will tell you that this is an invariant measure. So if you take any bunch of conserved quantities, you take the manifold where they take some specified values, and then the uniform distribution will be an invariant measure. Okay, so if you're lucky, you know all the conserved quantities in integrable systems, then you will probably have something ergodic, but although that may not always be the case. So for instance, for the nonlinear Schrodinger equation, the mass, which is the L2 norm squared, and the energy, which I defined, these are conserved quantities. So if one can define the uniform probability distribution on the space of all functions with mass m and energy e, that doesn't quite make sense. How would you define this? But in any case, if one can define such a thing, this would be an invariant measure for this flow. Okay. So just a little bit of history. This has a long list of people working on this. This was not exactly this invariant measure, but a weighted version of that, which is called the canonical ensemble. It was initiated by Lebowitz, Rose, and Spear, and then Bourgain proved that the measures that they had were invariant, and so did McKean, and various other people have worked on it recently, so I will not go into all that. So this has a history. So they're studying these invariant measures for these nonlinear Schrodinger flows. Okay. So how do you understand this? How do you make sense of this? Okay. So let me start with a very simple thing, which is a classical example. You take a uniform distribution on the simplex of all positive real numbers which sum to n. Okay, so that's a simplex in Rn. That's a standard simplex. And it is known that if you choose a point uniformly from this set, then the coordinates behave like IID exponential random variables with mean 1. Okay, so that is a standard result. And the reason why this happens is that if you take IID exponential random variables, divide by their sum, divide the vector by the sum, then that's uniformly distributed on the unit simplex. Now the sum is concentrated. The sum divided by n is close to 1. So the vector itself is close to this. So this is a standard probabilistic result which you can try to prove if you don't know this, that if you choose uniformly from here, the coordinates are approximately IID exponential. Okay, so another example, sum of squares equals n instead of the sum. Okay. So in this case, the coordinates behave like IID Gaussian, normal 0, 1. Okay. So again, this is easy to prove. You take a bunch of normal 0, 1 variables, divide by the norm of that vector, you get something uniform on the sphere. Now the norm is concentrated in high dimensions, and that's why the coordinates are approximately Gaussian. Okay. So these are classical results. So these are both manifolds defined by one implicit equation. Okay. So now my interest is in manifolds defined by multiple conserved quantities. So if you have more than one conserved quantity. Okay, just the very simple thing. You take all points, positive real numbers, so that sum to n, sum of squares is some b times n, where b is some constant. Okay, just a toy version of the problem that I mentioned, that all functions with mass equals something and energy equals something. So what happens in this case? Okay. So this, first when I was trying to study these invariant measures for these nonlinear Schrodinger equations, it seemed too complicated. So this, I started as a very simple toy example, and already in here, you see very interesting things. If you choose a point uniformly from this set, you see interesting things. So this, you can construct artificial some flows where these are the conserved quantities. So this will be an invariant measure in this set anyway. So how does this uniform distribution behave when n is large? Okay. So first of all, we note that B must be 1 or larger for this to be non-empty. By Cauchy-Schwarz, simple. If B is exactly 1, it's not interesting. All the xi's must be all equal to 1. So B is strictly bigger than 1 is the interesting case. Okay. Okay, so here is the, it turns out there is a phase transition. So here is the uninteresting case somehow. This is a subcritical phase. So remember, we are choosing x1 to xn uniformly from all positive numbers satisfying summation equals n, summation xi squared equals b times n. So suppose b is between 1 and 2, and x be a vector chosen uniformly from this manifold. Then there exists unique r and s, two real numbers, so that if you take the density proportional to this on the positive axis, it has first moment 1 and second moment b. So there is a unique r and s that is solving this. Let z1, z2, etc. be IID random variables following this density. Then for any fixed k, this random subvector x1 to xk converges to this in law, and these are all exchangeable. So basically, any k coordinates converges to IID from this distribution. Okay, so that's reasonable because the sum is n, sum of squares is bn, so you expect IID things with mean 1 and second moment b. And the largest one is not very large either. So if you take the maximum, if b is strictly less than 2, the maximum is like square root log n or less. And if b is 2, then the maximum is like log n or less. Okay. So this is okay. I mean, this is nothing very surprising. It's just like in the case of the simplex or the sphere. You choose a vector uniformly from this manifold. You get a vector with approximately IID coordinates according to some distribution. Okay. The interesting thing happens if b is bigger than 2. So if b is bigger than 2, then the following happens. Any finite collection of coordinates behaves like IID exponential random variables with mean 1. However, exponential with mean 1 has second moment 2. So how can the sum of squares be b times n instead of 2n? It's because there is exactly one coordinate which carries all the extra mass. So m squared over b minus 2 times n, this converges to 1 in probability, where m is the maximum. Moreover, the second maximum is pretty small. m2 squared, the second largest coordinate, divided by n goes to 0. So there is exactly one which carries all the extra mass. You have n minus 1 of them like IID exponential with mean 1. And there is one which carries all the extra mass. So this is what I call localization in the first slide. Okay, so in this phase, the uniform distribution on this manifold becomes localized. Okay, so this is a prototype, or this is it's a very simple toy model where you see the localization. So these solitons that appear is a very complicated version of this localization phenomenon that you see right over here. Okay, so I'll go into that. Any questions? Okay, so I'll tell you how to prove this and why this happens. So this is a toy model, so I can do that. Yes. Okay, so remember that x1 to xn were chosen uniformly from the intersection of the simplex and the sphere. Summation xi equals n, summation xi squared equals bn, and b is strictly bigger than 2, then this happens. Okay, so I will show you the proof later on, and the proof will show that this localization must be typical in manifolds with multiple conserved quantities. So if you have multiple implicit equations which define a manifold, and you choose a point uniformly from there, it is likely that you will get some kind of localization. Okay, so we'll see why that's the case. So as I mentioned, the soliton resolution conjecture, this itself is a localization phenomenon. So if you believe that this limiting behavior of this flow is like a pick from an invariant measure, okay, from an invariant measure, and the invariant measure is defined by this conserved quantity. So by Liouville's theorem, it's uniform on a set. It must be a restriction of a uniform distribution. So it's a uniform distribution on a manifold defined by multiple conserved quantities. So you under favorable conditions, you expect certain localized features to emerge. But why exactly solitons, that's not so clear. So I did some second level toy example in a previous paper where localization was proved near cubic discrete NLS, but a continuum limit could not be taken. So again, you see exactly one point where it's large and it's small elsewhere. But we could do a whole bunch of things with a simple, the parameters were in the regime where things actually became approximately independent. And more recently, so this is very recent, so I could finally prove what I was trying to prove. So this is the main result that I'm going to present, and it's in the next slide. And I cannot state this precisely because I need to define a lot of things, but I can state this roughly. So consider the d-dimensional focusing NLS, the nonlinear Schrodinger equation with nonlinearity parameter p. Okay, so I'll go back to the equation just to show you what it is, if you have forgotten. Suppose that p is less than 1 plus 4 over the dimension. So this is what is called subcritical nonlinearity. And that E is a real number bigger than the minimum possible energy at a given mass. So you have the energy and the mass defined before, and E is bigger than the minimum possible energy, so that there is at least one function in this energy at this mass. If we attempt to choose a function uniformly at random from all functions satisfying these two constraints, and how do I do this? I discretize the problem. Instead of the continuum problem, I take a discrete grid, define a discrete mass and discrete energy, which corresponds to the mass and energy of what is called the discrete nonlinear Schrodinger equation. So I discretize everything and make it also finite volume. And then I take the volume to infinity and the discretization to 0. Then the sequence of discrete random functions that you get, okay, they converge in sup norm to what is called the ground state soliton. Okay, so they converge to the ground state soliton, the soliton at minimum energy. Okay, so in what sense this convergence happens? How do you take this infinite volume continuum limit? So how do you take the volume to infinity, discreteness to 0, etc.? So these are all. I'm going to skip all that. Yes.
The limit is deterministic.
Yes. Yes. So it's like a shape theorem. It is a shape theorem. So you have these random functions, but in the limit, it's a deterministic soliton, what you get. Okay. Any questions? Yes?
Can you say a little bit more precisely what you mean passing the volume continuum limit?
Yes. So, okay. So what I have is instead of the whole of the space RD, I have a box of size L. Okay. So that L is going to infinity. And instead of actually the box, you take a grid inside the box of width h. Okay, so there are two parameters, L and h. Okay, so now on that grid you define an analogous problem, and you pick your random function and everything, and then you send L to infinity and h to 0. Okay, the box size is going to infinity and the grid size is going to 0 simultaneously. And one of the shortcomings of this theorem is that I cannot do it arbitrarily. So I say that there is a sequence along which L goes to infinity and h goes to 0, such that this limit exists. So I cannot say that arbitrarily if you send L to infinity and h to 0, the limit will exist. Okay, so that's a big shortcoming somehow. And the other shortcoming, of course, is you would ideally like to send h to 0 first. You would like to have an invariant measure on the torus. That I don't have. So nobody has actually. In dimensions 3 and higher, no one knows how to construct a continuum invariant measure for the NLS. So it has been constructed only in 1 and 2 dimensions by Bourgain and McKean and others. But in 3 and higher dimensions, except in one case, which is the cubic NLS, defocusing cubic NLS, where there are these 5-fold field theories which allow you to construct an invariant measure. But other than that, in dimensions 3 and higher, no one knows how to construct an invariant measure for the continuum system. But for the discrete system, you can always do. If you discretize, you can always construct invariant measures, and then you can pass to the limit. And you get this, and you get a soliton. Okay? Any questions? Okay. There is one other motivation. So just to show you that this is not only about Hamiltonian systems, this is a general idea. Systems with multiple conserved quantities, you can have it in other things also. For instance, large deviations in random graphs. So I'll just state a problem. Again, this is a somewhat understudied area with a lot of opportunity. Consider the Erdős-Srény random graph G and P. Okay, so there are n vertices, any two are connected with probability P. Okay. Let T be the number of triangles, or some other subgraph maybe. What is the behavior of this upper tail? The probability that T is bigger than 1 plus epsilon times the expected value, where epsilon is fixed and n and p go to infinity and 0. So this precise behavior, this probability, what is the exact nature of this probability? This was an open question for a long time. In 2004, Kim and Wu, and simultaneously there was another paper by Svante Jansson and co-authors, show that for any fixed epsilon and p satisfying some condition that it's not too small, it's at least log n over n, you have that this upper tail, it's basically like e to the minus n squared p squared, but there is this factor that doesn't match. Okay. So the problem is almost solved except for this factor, and this persisted for a while, and this was solved recently. But any question about this slide? Okay. So you have this Erdős-Srény graph, and you take the upper tail, number of triangles, and you look at what is this chance, and these are the upper and lower bounds. So I proved a couple of years ago the things actually matched. So this was at the same time that I was thinking about this soliton thing, and there is a connection. So this log factor is not just some little technical thing that's there. Okay, there is a very precise reason why this comes. So the upper bound without the log was proved using, one of the proofs was using martingales, and it did not look at localization. So this log comes in because of what I call localization of triangles. So all these extra triangles, they come from some very localized region in the graph. Okay, they are not spread out everywhere. So this localization happens, and okay, so I'll get into more details, but the reason why you have this is that it's, again, you can analyze it as a system with multiple conserved quantities. So here, this conserved quantity is the number of edges and the number of triangles. Okay. So number of triangles, you see it's already there, and the edges appear because they appear in the probability mass function of the Erdős-Srény random graph. Okay. So the probability mass function of the graph is some function of the number of edges. So basically, you try to count a number of graphs with a given number of edges and a given number of triangles. So that's sort of how it goes. And again, this exhibits localization. That's why this log factor comes in. Because this is just one other piece of motivation about studying these localization phenomena. Okay. Okay. So here is a summary. I will go into the sketch of the proof later on, but just let me give you a summary of what I've talked about. So I'm claiming here that it's natural to study uniform probability distributions on sets defined by multiple equations. Okay. So you have multiple equations, multiple constraints, and this defines certain sets, and it's natural to study the probability distributions. So such sets arise as invariant manifolds for Hamiltonian flows with two or more conserved quantities. Okay, and the uniform distributions are invariant measures for these Hamiltonian flows. It can also arise in discrete problems, right, like random graphs, where you're trying to study graphs with various constraints, number of edges, number of triangles, other constraints together. So you're trying to understand the uniform distribution. And it's the case that often this sort of measures exhibit localization. Okay, so it will be clear why that happens when I give a sketch of the proof. But a commonly occurring feature is that you get localization, and that somehow determines the nature of the problem. And the thing is, the progress has been made only in a few special problems, but many questions remain open. So I'll just show you the 4 papers that I have on this, and plus those papers have these references. So these are the 4 papers that I have till now on this line of thought. And you will see many more references to the literature from these manuscripts. Okay, so these are all our archive, so it's easy to find. Now, there are some possible research directions, which is you analyze invariant measures for other Hamiltonian systems. So the nonlinear Schrodinger is just one. Okay. There are hundreds of Hamiltonian systems. There are integrable systems where you know all the conserved quantities. So you can naturally try to study invariant measures for these things, and they will give you an idea of the long-term behavior of these flows. Okay, this one I don't know how to do, how to connect these invariant measures to the dynamics. So that's a general broad question. Once you know something about the invariant measures, how would you connect it to the dynamics? In sparse random graphs, large deviations for sparse random graphs, this is not too many theorems. Many open questions. So we have it for triangles, and some other authors have it for cliques later on, but general subgraph counts and other things. There are other models, exponential random graphs, geometric random graphs, power law graphs, all kinds of other models. So this is all open. So large deviations for sparse random graphs is generally not too many results. Okay, any questions before I move on to give you some idea about the proof? Okay, so how do you understand? So we'll just consider the toy problem, the intersection of the simplex and the sphere. Okay, just consider the toy problem. Why do you have this phase transition at b equals 2? Why do you have this localized value? So, and I hope that this will allow you to take something back from the talk, some amount of math instead of just some statements of some theorems. So suppose x1 to xn are IID random variables with a common distribution function f. Okay, and this is continuous CDF. Okay, so even if you have lost track, you can come back. Now it's what I'm going to show in this slide and the next few is a very simple line of argument. Let f hat be the empirical distribution function. So f hat of t is the proportion of values that are less than t. So this is something that statisticians use all the time, empirical distribution function. So now, by the law of large numbers, we know that if n is large, then f hat is close to this f. And in fact, one can show that the deviation in sup norm, as long as you have a continuous CDF, is exponential. Bigger than delta is minus constant delta times n. So the constant may depend on f, but it's always exponential. So it doesn't, even for heavy tail distributions, everything, there is an exponential deviation. Okay, so this f hat is indeed very close to f. Now you ask the question, what is the behavior of this f hat condition on the rare event that the sum of the xi's exceeds the expected value? So the sum of the xi's is, by the law of large numbers, it's approximately n times the expected value of x1. So if you fix an epsilon positive, and you condition on this rare event, what is this f hat going to be? What is this empirical distribution going to be? Condition on this rare event. Okay, is the question clear? So you have these IID variables, you construct the empirical distribution function, and you ask the question, what is this going to look like? Condition on the rare event that the sum of the xi's is bigger than, significantly bigger than what it should be. Okay? So one can show, I'll not go into the proof, that if these are IID exponentials, then condition on this rare event, f hat is no longer close to f. It's close to the distribution function of an exponential random variable with mean 1 plus epsilon. So it remains exponential, but it just becomes 1 plus epsilon. Okay, so this I'll not prove this because it's not so relevant to what I'm talking about. But in particular, conditioning on this rare event has a probability that the empirical distribution changes substantially. So there's a substantial change in the empirical distribution of the xi's. Okay. So this is quite common when you have exponential moments. When Ofer mentioned that you have Brownian motion conditioned to be very large at the end point, then it becomes like a straight line. So it just means that the summands are changing completely than what they were before. Okay. So this is often the case that you change the sum, you condition it to be pretty large, and then everything changes. F hat changes. However, this need not always be the case. Now suppose the tail of x1 decays slower than exponential. Let's say like e to the minus square root of t. Suppose the tail decays slower than exponential. Then what? Let A be this event that summation xi exceeds its expected value by 1 plus epsilon. And B be the event that the difference between f hat and f bigger than delta, where epsilon and delta are fixed constants. Then the probability of this event, A, okay, it's lower bounded by the probability that x1 exceeds this. Okay, so one element can exceed, the whole sum. That will imply that the total sum, these are non-negative variables, the total sum will exceed this. Now, since you have this sort of decay, it will be bigger than e to the minus some constant depending only on epsilon times square root n. Okay, so you get a lower bound on this probability, on the probability of this rare event. However, this upper bound on this event doesn't change. No matter what it is, it's a continuous distribution. It's still exponentially decaying in n. So what this means is that the probability of B given A, of course, is less than this. It's a very simple bound. And it'll be less than this because this is less than this and this is bigger than this. Okay? So it's going to be very small. So what does that mean? It means that conditional on this rare event, the empirical distribution is still close to F with high probability. Okay? It's still close to F. So you have this bunch of values and you draw their histogram, and even if this rare event happens, the histogram still looks the same. Now, how is this possible? The histogram, it represents the distribution, so the sum should be like a sum from that f hat. So the only way this can happen is that the extra contribution to this sum, this epsilon times expected value of x1, this extra contribution must come from a small set of values. Okay? So it must be that this full extra contribution comes from a small set of values, because most of the others, if you draw the histogram, it just looks like as if they were distributed like the original F. Okay? So any distribution where the decay is slower than exponential, you will have this phenomenon. Okay? So this is localization. A very simple example of localization that's going on here. You take some universal feature like this empirical distribution which characterizes what the values are, and then you show the probability of that deviating substantially is much less than the probability of your rare event. Then the rare event must be happening due to some abnormal values. Okay? Any questions? That's the first step. Okay, this observation. So how do we use this in the simplex sphere problem? So recall, we wish to study the uniform distribution on this set. All positive numbers which sum to n, whose sum of squares is bn. And we'll use this heuristic to show localization when b is strictly bigger than 2. So the uniform distribution can be obtained in a two-step procedure. First, you choose a point uniformly from the simplex, and then condition that point to belong to the sphere. And then conditional on this event, this is uniformly distributed on this set. Okay, so you first choose uniformly from the simplex, then you condition it to belong to the sphere, and then you have it. Okay. Any question? Now, we know that since this is chosen uniformly from the simplex, the coordinates behave like IID exponential. So you can use this to reduce the problem to to understanding the conditional behavior of a vector of IID exponential random variables given that the sum of squares is b times n. Okay, instead of the original problem, you can bring it down to this problem. Understand what do a bunch of exponential random variables behave given that the sum of squares is b times n, where b is strictly bigger than 2. Okay? Now the square of an exponential has an upper tail that decays slower than exponential. So basically it decays like this. Okay? So when you're conditioning, and the expected value is 2. Expected value of the square is 2. So this shows what's going on, right? Connected with the previous thing. So if b is strictly bigger than 2 and n is large, what we argued shows that if you condition on this rare event, then this rare event happens because of localization. So your summing squares of exponentials, whose decay is less than exponential, it's decay slower than exponential, the tail decay, and therefore you condition on the sum being large. By this previous argument that you have, it must be due to a very small collection of large values. Okay, and it's quite a bit harder to show that there is exactly one value that contributes, but we'll skip that. Okay, so this is a simple example of how you can prove localization under multiple conserved quantities. Okay. Okay. Any questions? And this also shows why the phase transition happens at 2. Okay. So if that is clear, let me also tell you a little bit about why this happens in triangles. So you have triangles in an Erdős-Srény graph. Let A be the event that the number of triangles exceeds its expected number of triangles by 1 plus epsilon. Now, as before, you lower bound the probability of this event by constructing something that implies that. So what you do is just you take a small number of vertices, construct a clique, and the probability of that is the lower bound for the probability of this. So lower bounds on probabilities are easy to obtain by constructing suitable events which imply the event that you're interested in. Okay. Now for each edge, consider the number of triangles containing that edge. Okay, edge meaning not edge in the graph actually, edge in the complete graph. So you take any pair of vertices and you construct the number of triangles, consider the number of triangles containing that. And let n be the number of edges which support too many triangles. Okay, support too many triangles. And let b be this event that this number is pretty large. Okay, that this number is not n squared, but it's kind of big. And then you show that the chance of b is negligible compared to this lower bound and the chance of this event, from which it follows that the probability of this conditional thing is small. Okay, so this will imply that condition on this with high probability, most of these extra triangles that you have are in a small region. Okay, will be in a small region supported by a small number of edges. So this is a very simplified version. So the actual proof is much more complicated there, and it was simplified later on by DeMarco and Kahn. So the general idea is that in these localizations is that you take your rare event that you're conditioning on, you get a lower bound on the probability, and then you show that in the original system, you consider a certain feature of the original system which is very stable, which is such that the chance of that deviating from the expected behavior is much smaller compared to the probability of the rare event. So that will show that most of the system stays as it is, even if the rare event happens, and only a small part will change. Okay. So that is sort of all. I would like to talk about localization in these nonlinear Schrödinger flows, but unfortunately, this is a lot to summarize in one slide, and just for the students here, you can take a look at this. I'm trained as a statistician, so I don't know so much math. I was happy to learn a bit of math doing this, and maybe you will too. There are a whole bunch of PD and harmonic analysis things. So that's for today, and tomorrow I'm going to talk about what was promised in the abstract. So that's what I'm going to talk about tomorrow.